In this lesson, we're going to discuss slope fields. And slope fields are effectively a way to understand the way that a derivative is behaving, and then, of course, consequently, the way that a potential solution to a differential equation is behaving. That is to say, to see a family of functions or a specific function that would satisfy a certain differential equation. So the first differential equation we're going to start with is this one, y prime equals 2x plus y. Again, it's a first order. In order to draw a slope field basically is a collection of little line segments that show you the slope at any given point. So for example, if we substituted in x is 1, y is 0. So that's the point 1 comma 0. We would find 2 times 1 plus 0 is 2, which means the derivative is 2 at that point. So I'm going to go to 1 comma 0 and make a little line segment with slope 2. Now, how do you know that that's slope 2? Well, I mean, I'm just kind of drawing it as close as I can. Remember that a slope 1 should have a 45-degree angle. So I think it's something near a slope of 2. We'll just do some of these. 2x, let's do 2 comma 0. 2 times 2 plus 0, that's 4, so that's going to be steeper still. 1 comma 1, for example, that would be 2 times 1 plus 1, that's 3, so that's going to be steeper. And it's very hard to get these things exact, as I'm sure you can tell. 1 comma 2 would be a slope of 4. So you can see that that point has a higher, that point has a higher derivative than that and than that. And even 0, 0 has a slope of 0. So I'm just going to leave a little line segment there to say 0, 0, the slope is 0. 0, 1 would have a slope of 1, which if you look at my lines, it is noticeably, this one's noticeably less steep than that one. 0, 2 would have a slope of 2. Again, less steep than that one. And you start to get an idea for how this thing is behaving. We'll do a little bit more of that in a second. Negative 1, 1, that would be negative 2 plus 1 is negative 1. So something like that. And that little downward slope might have surprised you given the way this was all moving, but we'll just keep going. Negative 1 comma 2, that would be a slope of 0. Then we could do negative 1, 0 would have a slope of negative 2. Negative 2, 0 would have a slope of negative 4. Negative 2, 1 would have a slope of negative 3. Negative 2, 2 would have a slope of negative 2. And like I said, this is not, there's no exact science to the way I'm drawing these lines. I'm just trying to contextually or relatively to the next ones make sure that they look just about right. You can see here there's very little difference between those two, but it's just a matter of me not being precise like a computer would be. 0, negative 1, that gives us a slope of negative 1. 0, negative 2 gives us a slope of negative 2. Then 1, negative 1, that'll give us a slope of 1. 1, negative 2, give us a slope of 0. And then 2, negative 1, that's 2 times 2, minus 1, is 3. And then 2, negative 2 would be a 2 slope. So now, for example, if you were also given Well, let's finish. No sense in not doing that. -1, -1, that would be a -3 slope. -1, -2 would be a -4 slope. And then -2, -1 would be a -5. And -2, -2 would be -6. And I guess I left these two off. 2, 1 would be 5, and 2, 2 would be 6. So anyway, again, I tried to just draw it somewhat accurate. It's not going to be perfect. But you can see the way that this function would behave. So now, for example, if you were given a separate condition that said y of 0 is equal to 1, then you would go to 0, 1, and you just basically follow the trajectory of the way that this slope field takes you. So in this case, it would kind of look something like that. Right? So, and there's all kinds, you can start anywhere. If we started here, for example, maybe it would kind of look like that. So, and that point, the second one I did was 1, 1. So that might have been if you were given the initial condition that y of 1 was 1. But the point is, you get an idea for and you can see they're all going to be similar. So you'll get an idea for the family of functions that satisfies this. And if you're thinking, what's this business about a family of functions? Well, remember that a certain a differential equation can have a solution that has blah, 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 plus c. And it gets shifted up and down, right? Or potentially all other changes. But this thing generally has this shape. No matter where we start, the slopes are dragging us down, 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 down. Generally, we're getting flattened out somewhere in this area. And then we are sent upward. So it's just one way to represent the solutions to a differential equation, whereas last lesson we just abstractly wrote the solutions to the differential equation. So here we've got a graphical approach. Now I'm actually going to show you 3 different slope fields that are computer generated, and we'll just play a little matching game to see if you can follow me. Take the lights down. Hopefully that is visible for you. Good shade. So if you can see those, the goal is that you match each one of these 3 bottom differential equations with one of the 3 slope fields. And just a way to do that, for example, if we look at this one, is just point-wise testing them, and you'll get a feel for how they work a little bit better. So, for example, if you plug 2 large positive values in for x and y, it should be very positive. And all of these have that in them, right? The higher positive values, like 2, 2, would be a slope of 4. Okay, I could believe all of those having slope 4 there. So maybe you go to these points, which are they seem to be all flat on the y-axis. So in other words, if x is 0, we should see 0. If x is 0, well, it's not necessarily 0, because y could be higher. For example, at 0, 2, this thing says 0, but 0 plus 2 is not 0. So you'd go to a different one and you'd say, okay, 0, 2, could be this, could be this. So now you find another place. You can see for example, in this slope field, things tend to flatten out as you get closer to a 0 y value. So for example, down here, if we did -2, 0, -2 plus 0 is -2, but that says it's 0, which means this x plus y must match with this slope field. And again, you can test some more points if you're not quite sure. For example, negative 2, is 0. Negative 2, positive 2 is 0. So negative 2 plus 2 is 0. So that further confirms that Roman numeral 1 matches with slope field B. Now if you look at, let's say this one, y prime equals y. That says basically that the slope is going to match the y value. And it's just as simple as that. So this one could be it, or this one could be it. So let's say, let's just test a certain point. We already said 0 here meant this was 0. So if y is 0, oh yeah, that whole thing is 0. So that's starting to make some sense. Also notice all the all the y values of 2 all have the same slope. All the y values of 1 all have the same slope. All the y values of a half all have the same slope. All the y values of 0 are 0. So it seems pretty apparent that that one matches. And then if you take y prime equals x, this means for a given x value, let's say x equals 2, all the slopes should be 2. Okay? And when x equals 0, right? Now I want you to actually think about what the solution to that differential equation would be. Y prime equals x. It would be, if y prime is x, take the antiderivative, so take a second and do that. You should get x squared over 2 plus c. Well, what shape does x squared over 2 plus c have? It has x squared type shape, a little bit flatter because it's 1/2 x squared. And that's parabolic. And if you look at this slope field, you see the parabola is being carved, and you might think to yourself, yeah, but what about the plus c? Well, that's what shifts this thing up and down along the y-axis. So you can see there's a very clear tie between the original differential equation, our abstract or our sort of algebraic or antiderivative type reasoning with it, and then its picture of its slope field, which generates a family of curves. Because we could draw curves along this, and they would all be, all the slope fields would, if we started at a certain point, would force us into a certain shape. Okay, so from there, if you ever needed to sketch a slope field, I would probably just use, well, let me show you an example. If you are asked, this comes from the Stewart textbook, if you're told that y prime, let me make sure that you can actually see this. I'll move it down so that you can. Okay, if you're told that y prime is x squared plus y squared minus 1, you just have a bunch of x, y combos, substitute them in, and then this says y prime equals, and then just do the calculation. So simple stuff, make a table, and from there, you could take all those values that you got for y prime. This, by the way, is on page 573. You take all those values for y prime, and you could make a picture of the slope field, just like this one is. You can see that there's some interesting behavior around the origin. And now if you wanted to see the family of functions, you could just pick different points and create families of functions. In this particular example, we were asked, or the textbook asked the reader, I guess, to have y-intercepts -2, -1, 0, 1, and 2. So they started at those points, and then they just allowed the slope field to take them in whatever direction it did. So there's 1, 2, 3, 4, 5 in there. The last two are sort of hung up. So that is a brief lesson there on slope fields.